as you guys left yesterday, I asked you if you would make sure to take a minute and find out what the three motion equations are for an object that's in simple harmonic motion. Did you have a chance to do that? Oh, I gave you one of them, didn't I? Because it wasn't just simple harmonic motion. We were talking specifically about the pendulum. So I said theta as a function of t was theta max times cosine square root of g over L times t. And I suggested there might be two others, and that they would be similar to the one for a spring mass system, but with a pendulum. So one with like omega in it, and one with alpha in it. Any takers? Bring it on, I'm ready. I got the rest for you. Good job. Yep, that's it. You're going to do just the same thing you had before. Anybody want to get acceleration for me? Got it. All right, perfect. Which suggests, of course, that this should be telling us omega max, and this should be telling us alpha max, the maximum angular velocity and the maximum angular acceleration. For a pendulum, so this is an object that has a fulcrum at the top, and is oscillating back and forth. Now, the repercussions of this is that when all of this is advanced by 2 pi, our object recycles, meaning it goes back to the start. So one full pattern of it oscillating is when the inside of that has advanced by 2 pi radians, which is why the period comes out to be 2 pi times the square root of L over G. And the frequency has to be the inverse of that. So, this is really the book on pendulums, but the thing about pendulums and the spring mass systems is that we've already done problems with these before. Problems involving conservation of energy. I don't want you to fire up these equations. No, you're probably never going to need these for most everything having to do with simple harmonic motion. I want you to be aware of them, but this is the vast majority of the focus that they're going to have. And just because, I'm telling you that a pendulum has a weight on the bottom, and that's what a pendulum looks like, you think that all of this is just about pendulum systems, or just about, spring mass systems, or all just about oscillations. Look, there's the distinct possibility that I could say, all right, I have a box, I pull it back against a spring and compress the spring. And then what happens when I just let it go? Well, if the box isn't connected, then this just launches the box. The oscillations occur because the box is connected to the spring. And because the box is connected, it oscillates, because once it gets to equilibrium, the spring starts pulling back on the box and slowing it down. That's why you're noticing in your homework there are enough questions like you pull the pendulum back and it's asking about how fast it might be going when it makes it down to the bottom. Well, that's not really a pendulum question. That's the object had gravitational potential energy here, and when it swung down to the bottom, it has kinetic energy here. So don't be fooled by some of these questions that are making you think you're going to have to do some, fancy oscillating stuff. You are in music to know that there's all sorts of different kinds of ways to make things vibrate, and there's all sorts of ways for things to be in oscillations. Let's see if you guys recognize this, because I have a lot of music kids in this class, and I'm sure that some of you have seen one of these before. And I know I'm taking care to draw this slowly because I really would like it to be recognizable. Who's seen one of these before? They go back and forth. Do you know what it's called? That's right, metronome. A metronome is an upside down pendulum. If you've ever seen one, you know it's got markings here. The markings here corresponds to beats per minute. And you slide the weight backwards or forwards to determine how fast it's going to oscillate. A simple metronome. It's just a pendulum. So not every pendulum and every spring mass system has to look the same. There's all sorts of systems that obey these same kinds of simple harmonic rules that don't look like a spring pushed up against a mass. In fact, it's funny because I have my hair tie in my fingers right now because I was using it for some tutoring just a few minutes ago, actually. And almost anything you grab that has any kind of elasticity can suddenly be a spring mass oscillator, or it can be something that is springy. Has anybody ever, with a rubber band, chucked paper across the room with it? No. I thought we were all in middle school at one time. Seemed like the thing to do. You get that rubber band, you get that little piece of paper, you fold it up into a little square, and you grab that thing and you pull it back and you wait till your teacher's not looking and you pow right across the room. Really? You guys didn't do that? I think there's some liars in the room. I see some hands up because maybe this is, you were never cool. This might be a little bit of me just, assuming a non-gender neutral environment, but boys do that kind of stuff all the time. Girls do too, but they don't want to be caught doing it. Boys really don't care. They want to be caught doing it. Yeah, they're like that. Well, okay, so what I do want to talk to you about today in a little more depth is something about pendulums specifically that is a little weird. And I also want to spend a few minutes demonstrating where the F equals KX part of a pendulum comes from. Because remember, as I said to you from the beginning, any object in simple harmonic motion must obey this relationship. Now, it's not that by itself. It's the knowledge that there is an unbalanced restoring force that creates an acceleration that is proportional to the displacement. So this leads to this function, which we know is a second order differential equation. That's what we learned about a couple days ago. That's what I called it. It's when we did the calculus part, and I wrote this as a calculus expression. Right? I know it looks weird for those of you not in calculus, but that function, the idea that the acceleration is related to the displacement, is incredibly important here. And this is not arbitrary. Acceleration has to be there, displacement, a negative sign, and a constant. Those four things are all incredibly important for this, because something is not a simple harmonic oscillator if those conditions aren't met. And I need you to, I really want to relay this to you, that the relationship between the acceleration and the displacement has to involve some physical constructs, something about the shape or size of the device. That's what's here, K and M. K has to do with how springy the system is, and M had to do with how much inertia it had. So I'm being very clear that there must be somewhere in the pendulum this same kind of idea. Now, to see that idea is going to be hard because there are some things about it that just don't work out the way we would like, which is why pendulums are a little weird. And to appreciate this, I'm going to try and take my time on it and draw my pictures carefully. But we are trying to see where in the pendulum we get the acceleration proportional to the displacement. That's what we're looking for. And we know it must be based on only two forces that act on the system, because we talked about those two forces. The weight and the tension are the only two things that are occurring here. Now, before I go on, before I do anything else, I need to tell you from the get-go that there are lots of systems like this. And so whenever we are faced with a system that looks like it's oscillating, one of the things that engineers try to do is try and model the oscillations. We're going to take a look on Monday at failed systems and unique systems that vibrate, with one of them being like the Tacoma Narrows Bridge, which is famous for failing. It was a bridge that fell in the wind, but it didn't fall because the wind was blowing so hard. It fell because it vibrated itself apart. And you can see it doing it in real time because they caught video of it when it occurred in the 1920s. Buildings are constantly swaying in the wind. They are designed to move and oscillate, but they're also designed to ensure that those oscillations are dampened. So engineers who build those buildings have to know the frequency of those oscillations and what's controlling it so that they can build in safety mechanisms to try and dampen those harmonic oscillations, but not to zero, because the buildings have to be able to be flexible in the wind. Anybody been to a tall building before and felt it moving in the wind? You know it's very unsettling in the beginning. I mean, I can never get used to it. I mean, I don't spend a lot of time on those, but still. So we look for the ways in which these things behave and try and find this thing that controls it. We know for a spring mass, we can control it. We know how the mass and the spring constant interact. So now for bigger systems, we try to find what controls it. So I'm going to give you guys a chance to answer this question. Would you prefer I do this in terms of force or do this in terms of torque? Force needs a thumbs up in the participant window, and torque gets a thumbs down. You tell me whether you'd prefer me to do this from the standpoint of torque or force. I'll give you a second to decide, and whatever one gets the most votes. So it's force is thumbs up, torque is thumbs down. All right, it's 31-8. I'm not going to wait much longer, so we're going to go all the way. We're going to do force. Okay, so to understand this, there's a few things I think we should set up and establish. First, the system has been displaced theta, and we're about to let it go. Okay? So I've displaced it a little bit to the left, and I've just let it go. Now, I want to be very clear. Let's say that theta in this case would be positive, that direction, which would mean anything going in this direction would be negative. That okay? Just establishing direction. I know that I have two forces here. Mg is one of them, and tension is the other. Now, here's where it's going to get a little funky. And I'm not trying to make this hard, but the pendulum doesn't actually travel along this line back to equilibrium, does it? In fact, I think you all realize that it would have to travel along a curve back to equilibrium. Does that make sense? This part's actually really important. So before we go on from this, I'm going to label this curved path S because it's an arc length. And I'm going to label this dotted line path X because it's the straight line distance. Is that okay? Now, here's why this is important. If the length of the string is L, I see a right triangle. Do you see it? So the sine of theta would have to be opposite over hypotenuse. You guys see that okay? Now, this one might be harder for some of you, and I'm just going to solve this for X just so I have it written the way I want it. The arc length, S, I can find it out because I know what theta is. And what I mean is, if you remember back, delta X equals R times delta theta. Do you remember that from things that are in a spinning or something like that? I want to find out how far they travel. It's the arc length times the radius. So in this example, S is an arc length. And its arc length would have to be equal to the radius, L, times the angle, theta. As long as theta is in radians. So the real question I have for you is, how different would these two numbers be? So for right now, tuck that away. Just tuck it in the back of your mind for a minute, okay? We're going to come back to that in a few minutes. But for right now, let's do what I said we needed to do, which was to analyze this. I'm going to draw in a coordinate system. I'm going to get this stuff out of the way so that it's not distracting me too much. And I'll draw those back in later when I need them. What I'm trying to do here is find a coordinate system that I can use to describe the unbalanced force acting in the system. I know that you'd probably like me to line this up with mg. And that would be nice, except when I release the bob isn't going to suddenly go this way. The bob is going to go this way, right? It's going to travel tangent to the circle. So I have to align my system with the direction of likely motion. I believe the object's going to accelerate along this blue dotted line. That's the direction I think it's going to accelerate. Tangent to the circle. Which means that I can establish right now that the net force in the y direction is going to be 0. It's not going to accelerate that way or that way. And I could write these forces in. It's not a big deal. This one, this would be mg cosine theta. Now, I'm skipping some steps, but this is theta right here. Right? Geometry. Those are corresponding angles. Not alternate interior or alternate exterior, but corresponding. Do you remember all those phrases? Corresponding, alternate interior, alternate exterior, vertical angles, all that garbage? Neither do I, clearly. I don't remember any of it. So that one's mg cosine theta. And so I could say that tension minus mg cosine theta equals 0. I don't need to do anything with that. That's not the direction it accelerates. So I'm going to jump to the next one, which is net force in the x direction. This one has to equal ma. All right, now I'm getting to it. I'm getting to that ma part, the ma part. So all I need to do is figure out what my force is that's causing that. And my force is this one, mg sine theta. Yay, mg sine theta again, our friend. Our friend from inclined planes. Oh, I missed him so much. I'm so glad he's back, mg sine theta. So that's the only force that's causing my system to accelerate. So I'm going to write this as mg sine theta equals ma. Good so far? Now wait. Theta is this way, positive. But my acceleration is this way, negative. Right? So I'm going to put my negative sign in here to remind me that the acceleration is in the opposite direction. The opposite direction of theta. I had to pull the weight out to the left, but the acceleration is clearly to the right. We all okay with that? I'm trying to make sure we're being consistent. I need to know that the direction that this is going is back to equilibrium. That this unbalanced force isn't causing it to move further away from equilibrium, it's causing it to move back to equilibrium. We good? We're like 2 minutes from being done. Because if you look, I've got some stuff here I can do. I want to get the x in here. So to try and get the x in here, I see a place where I can get the x in there. So I'm going to do some substitution. So I'm going to put one thing in for another. Is that all right with you guys? So x over L is going to go where the sine theta is. So minus mg x over L equals ma. Now, why would I write it like that? Well, because I'm moving it over here, but I'd like to line these things up. So it wouldn't like be terrible if I just said, ma equals minus mg x over L. That won't be terrible, right? I just want them lined up. In fact, I want to do more than that. I kind of want to go and put the L here. So I'm going to do that. That way, they look really similar, don't they? In fact, I'm going to grab and take away the M that was on both sides. And looky there. Right? You see what I see, right? You do see it, right? The whole G over L thing right there. Isn't it exactly what we wanted? I got the negative sign in there. They match up perfectly. And that's what we're trying to show. That if you can make your net force equation look like Hooke's law, then your object accelerates. That's what I mean when people look for that. They look to see if there's some possibility that a system might oscillate, especially systems that we don't want to oscillate. We look at how those forces interact. But there's a problem. It's not a huge problem, but it is a problem. Our object doesn't travel along x. Remember? Our object travels along s. So although we have shown that a pendulum has within it the properties of a simple harmonic oscillator, we based it on a lie. Because our object doesn't actually travel along x. It travels along an arc length. And they are not the same. So, we did all this work to show that this was a simple harmonic oscillator, just at the end for me to jump in and say, well, I'm just kind of lying to you, because that's not what it does. The question comes down to is, how different are those two lengths? Are they pretty close? In fact, if we compare these two things, do you realize all we're really comparing is sine theta and theta? That's all we're comparing. Well, thing I love about physics is we just say they're equal. Not because we want to, but because they are. I want you to try this real quick. Who has a calculator? Good. Make sure your calculator's in radians. Okay? So, you got your calculator in radians? Great. So, 10 degrees. How many radians is that? Do you remember how to do it? I don't want to spend a lot of time with it. Divide by 180 and multiply by 3.14. What do I get? .175. Can somebody take the sine of 0.175? Assuming your calculator's in radians. Is it a fluke? What's 5 degrees? Divide by 180, multiply by 3.14. Can somebody take the sine of 0.08? What, you said 17? Oh, 0.087. Somebody take the sine of that for me? We call this the small angle approximation. For small angles, theta equals sine theta, which means pendulums are simple harmonic oscillators only when their amplitude is small. We generally say less than 10 degrees. Less than 20 is still pretty close. You get outside of that, it is no longer a simple harmonic oscillator. It's called the small angle approximation. Well, folks,